Here's a data set of the incomes of US adults 15 and over. So there's some of these adults are very young in 2010, and many thousands of individuals. And you don't want to be drawing a stem leaf diagram because, as we said, the leaves are going to be falling off the screen and falling off your page. So even to look at these numbers, you certainly don't want to see them all on a screen or several screens. What you will normally be doing is tabulating them. And so here somebody has done that. Income has measured in thousands of dollars. This is annual incomes. So this group made between $25,000 and $50,000, and 27% of the population was in this group. That's how you read that table. And here you can see, even by just looking at the table, that about 3/4, actually exactly 3/4, had incomes in between nothing and $50,000, and 1/4 had incomes higher than $50,000. Now I have simplified these numbers because there are decimals and they're not so clearly whole numbers, but for now that'll do. So even looking at the table, you can get some sense of where the incomes are distributed, but really you'd like to do something graphical. Before we move to that, I want to examine the table a little bit more closely, because I know that there is something that is bothering some of you, and that is this person at the edge. The people who make exactly $25,000 or the people who make exactly $50,000. Where are they in the table? So if you look at people who earned $25,000, then they are either in the 10 to 25 bar or in the 25 to 50 bar. Which one do you think they're in? Want to have a go? Votes for 10 to 25? No? 25 to 50? You got a choice? You should not have a choice. You cannot possibly know because you didn't make the table. The person who made the table chose where to put these people. As it happened in this case, the decision was made to put them in the second interval rather than the first. And this decision has to be made every time you have a table of entries like this. And it is called an endpoint convention. So it is a convention, a policy that you follow about the ends of the intervals. And in this case, for this particular table, the statistician decided to use the following convention. Intervals include the left endpoint, but not the right. In other words, in the 25 to 50 interval, the people who made $25,000 are in there, but the people who made $50,000 are not. So where are they? They're in the next one. And that's a decision that was just made at the level of making the table. You are free, if you tabulate data, to have any convention that you wish. Just say what it is and be consistent. And that raises another question. If you add up all of these percents, you should get 100. And I'll say, by the way, since you know that I have simplified these data, I'm getting exactly 100%. Sometimes, you know, when you have decimal places and so on, when you add up, you might not get exactly 100. You might get 100.01 or 99.97. If you get 105, you should be worrying. Maybe you've done something wrong, but you could be a little bit off. For these data, the total percent is 100%. That means I've got everybody in this range, which raises the question, did nobody make 150,000 or more? Well, actually, lots of people did. In particular, some people like the Gateses and the Ellisons and the people who make $150,000 every time they turn around. They're all there. But it's just that there's very, very few of them compared to the rest of the population. And so there are so few, in fact, that their earnings have all been swept into this interval here. That's something that's very commonly done. When you have a very small percent that are very far out from the range of the data, you may sweep them all in to your final interval if you don't want your intervals to go out that far for such a small number of people. So just be aware that in tables like this, very often that has been done for the end bar. Now looking at that table, you have some sense of what the distribution looks like, but we'd really like to see it. We'd like to see it in a picture. And so what I'd love to be able to do is to draw a diagram that's like a bar graph to show how these incomes are distributed. And what does that mean? Well, we need a horizontal axis, and so we're going to show incomes on the horizontal axis, and we want vertical rectangular bars. So now I know what my horizontal axis is going to look like, and now I need to know how to draw the vertical bars, for which I need the heights of the bars. So let's go back and take a look at our data, and there's the same table again. And here's an interval 0 to 10, so I'll have a bar above that. Its percent is 20. I could plot 20, and I could plot 28 for the next one, 27 for the next one, 18 and 7, and I'd be done. But wait a minute. Wait just a minute. Let's take a look at what's going on here. The interval 0 to 10 is 10 units wide. The interval 10 to 25, on the other hand, is 15 units wide. 25 minus 10, 15. The one after that is 25 units wide, 50 minus 25, and now we have intervals of different widths, and now this gives me pause because I remember lecture 1.3 where there were those unequal intervals causing a lot of trouble when you simply plotted the percents above them. And so we have to be careful about exactly what we are plotting. If you remember from last time, we cannot plot the percents as the heights of the bars because the widths of the bars are unequal. Our eye picks up the area as the percent, and the width matters to the area just as much as the height. So we have to be careful. So how tall should the bars be? Let's work it out. Our idea is to look at one single bar, and if we can figure out how to draw the first bar, then we should be able to follow that method for all the other bars. And so our table says 20% of the people are in the $0 to $10,000 interval. And we know from lecture 1.3 that the area of the bar is what the eye picks up as the percent in the interval. From this, we should be able to figure out what the height of the bar ought to be, because we know that the area of the bar over that particular interval must be 20%. Well, what's a bar? A bar is a rectangle. What's the area of a rectangle? You all know what the area of a rectangle is. It's the height times the width. Exactly. And so it's the height that we're trying to find times the width of the bar. And what is the width of the bar? Well, the bar goes, the interval stretches from 0 to 10, which means its width is 10, and the units are thousands of dollars. So the width of the bar is $10,000. So what have we learned from this? We have learned from this that this 20% is equal to the height that we're trying to find times $10,000, and so divide through by $10,000, and the height that you are trying to find is 20% divided by $10,000, which is 2 numerically, with units of percent per $1,000. And this is how you find the height of the bar that you are trying to draw. You take the percent in your interval and you divide by the width of the interval. And if you want a formula totally nailed down, it's the percent in the interval divided by the right end, the large end of your interval, minus the small end. And here you have your first formula. There aren't going to be many formulas in this class, but this is certainly one of them. This is how you can calculate the height of the bar. And so, well, if you can do it for one bar, as we said, you can do it for them all. Here we go. Isn't it lovely having a computer? Bang! All the heights computed at once. So here's our old friend 2 again. We took the 20% here and we divided by the width of the interval, which is 10. 20 divided by 10 is 2. The next one, 28% divided by the width of this interval is 15. 25 minus 10. And you get 1.87. You can see that this bar, the second one, will be shorter than the first. And so on. And as it happens for these data, the tallest bar is the first one, and then they just keep dropping down. So shall we look at this in a picture? I think so, because this table has gotten even more complicated with a heights column. And here you have the graphical representation that we were looking for. It is called a histogram, and it shows you how the incomes are distributed over their values. When you look at any graph, it is a good idea to look at both axes carefully, and to start with the horizontal axis seems like a very good idea indeed. These are the incomes, and the person tabulating the data had made the choice to use the interval 0 to 10, 10 to 25, 25 to 50, and so on. And I hope you can see why they did not go ahead and just use equal intervals, 0 to 10, 10 to 20, 20 to 30, 30 to 40, and etc. First, because there have been an awful lot of them. And second, because you can see that as you have intervals over bigger and bigger incomes, the amount of data is quite small. And so maybe you don't want all that detail about exactly how many earned between 100 and 110,000. So this diagram gives you the flexibility to choose your intervals as you find convenient. Now, when you draw, it is important to make sure that the horizontal axis is drawn to scale. These are numbers. This is not green, blue, and red anymore. These are numbers, and they have relations to each other, clear mathematical relations. So the distance between 0 and 10 compared to the distance between 10 to 25, well, that's 10 units versus 15 units. So this second bar better be 1.5 times as wide as the first bar. And when you look at 0 to 25, that width should be the same as the width between 25 and 50. If you draw it any other way, then you have maybe a pretty picture, but you have mathematical nonsense on the horizontal axis. And if you have mathematical nonsense anywhere in your picture, you will have a lot of trouble giving a sensible mathematical interpretation to anywhere else in your picture. So step one, look at the horizontal axis and make sure that it is drawn to scale. And now we go up and we look at the heights of the bars, and what I can see is that this distribution is bunched up near the low end, lots of people with modest incomes, no big surprise there, and then a small number of people with large incomes. And in fact, really, this distribution goes on. It gets lower and just goes on like that. This is a very typical shape for an income distribution, going up and then coming down like that and tailing off. Certainly not symmetric, certainly not bell-shaped. Most people with low to middle incomes, a small percent with large incomes. We will see this over and over again. We will spend some time in the next lecture examining what the vertical axis means. For now, I just want to summarize the moves you make when you draw a histogram. What's a histogram? It's a figure that shows how a quantitative variable is distributed, and it allows for you to choose intervals of any length you please. Your intervals on the horizontal axis do not have to be equal. How do you draw it? Step one, horizontal axis. Horizontal axis. People focus on the heights, but you've got to get that horizontal axis right first. And then you know the main idea of the histogram is that areas represent percents. Areas are what our eyes see. And so we are going to use areas representing percents, which allows us, by a calculation we did, to compute heights as the percent in an interval divided by the width of that interval. The units of height are percent per unit on the horizontal axis. In our example, it's percent per $1,000. Now that is an interesting quantity, and we will look at it more carefully. What I want to say for now is that the units really matter. I've had students come to me and say, but I calculated the height correctly, it's so picky that you want units. And I look at their question and they have answered 12. Their height is 12. And I tell them, well, if I had written down 1 as my answer, would you have said that was correct? And they'll say, no, 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 the height is 12. Well, let's take a look at that. Their height was 12% per foot. Foot was the unit on the horizontal axis. That's 12% per 12 inches, which is exactly the same as 1% per inch. So their 12 and my 1 are both correct, but in different units. So if you just give me a number, the height is 12, I don't know what you're measuring in, and so your number isn't making a lot of sense. So the units do really matter. Please provide them.